Okay, and I'll edit it afterwards. All right, I guess we can get going. Hi, we're Team 16, and this is our final project for this course, optimizing cargo aircraft cost. For the overall system, the rationale for our system level design is to maximize the daily profit of an aircraft in a given scenario. Our system consists of 3 subsystems, including aircraft routing, aerodynamics, passenger, and cargo. The system boundary is defined at the operation site of the cargo, the aircraft itself, and the flight routes. This includes any fuel, crew, cargo, airport facilities, and maintenance resources involved. Few inputs and outputs for our subsystems. For subsystem 1, the aircraft routing, the output is to maximize total profit. A few of the inputs are relevant to the logistics of aircraft routing, including things like route data and airport costs. For subsystem 2, aerodynamics, that's all related to the liftability of the plane, and we're trying to minimize the drag coefficient to maximize fuel economy. Subsystem 3, passenger and cargo, we're trying to minimize the total cargo loading cost, and inputs relate to cargo and passenger information, aircraft performance, and aircraft performance limitations. A few shared variables include fuel efficiency depending on drag coefficient, and number of passenger seats and weight balances determined by cargo passenger balance. This is our system flow diagram. A few things to note here are that the passenger and cargo subsystem flow into both the aerodynamics and the aircraft routing subsystems. So you'll see those dependencies further on in the report.
So we begin with the key parameters, which includes total seating capacity, load factor, fuel price, and baseline MPG. Note that the aircraft speed is fixed, and we assume a symmetric airfoil with a fixed wing area. Several operation assumptions are embedded into the setup, such as a maximum cargo weight and flight level constraints like a maximum of 24 hours for the full schedule and a ground time of 45 minutes per stop. Additionally, the number of the crew members and their pay scales are defined based on loading efficiency, which becomes important in cost modeling later. On the right, you can see the main system level constraints, including lift to weight balance, drag limits, angle of attack, and the core bounds, as well as total aircraft weight and the loading time restrictions. Next. And mathematically, our objective is to minimize negative profit, which is equivalent to maximizing the system's 24-hour revenue minus cost. So the trade-offs are key here. On one hand, minimizing the drag coefficient improves fuel efficiency, but may result in structurally unrealistic for like heavy wing shapes. On the other hand, minimizing turnaround time improves routing flexibility, but adds to crew loading cost. In fact, that's the core difference from the midterm. So the subsystem model treated variable like fuel efficiency and weight as constants. Now they are linked and pass across subsystem. For example, subsystem 3 determines weight, which affects subsystem 2's drag, which then determines MPG, and finally MPG influence fuel cost in subsystem 1. Next. To support the formulation, we made several simplifying assumptions in the system model. First, flight time is modeled as a function of distance with constant crew speed and fixed ground times. All fuel costs are assumed to be identical across airports. Routes cannot be repeated, and each flight is assumed to have equal load capacity. For aerodynamics, we calculate both viscous and wave drag and assumes the use of new airfoil in analysis. So while they, this assumption reduce model complexity, they still capture the key coupling and trade-offs between aerodynamics operations and the remain subsystem. Next.
So for the overall system, the optimization construction is linearly. The sub problem can solve separately, and the results will pass to each subsystems. The subsystem 3 will be the first system to be solved. It will give the web balance to the subsystem 2, and also the passenger cargo ratio to the subsystem 1. The subsystem 2 is aerodynamic optimization. It will minimize the drag coefficient and give the fuel economy to the subsystem 1. Finally, we will solve the subsystem 1 based on the passenger cargo ratio and the fuel economy. Next. So for the modeling approach, the subsystem 3 was using the MATLAB to do a linearly programming. The subsystem 2 used a Python library to solve the aerodynamic problem. And the subsystem 1 used the Python library to do a integral linear programming. Next.
Here you can see the optimization method we chose to do for our project. We chose the multidisciplinary feasible formulation because of its ability to optimize individually for our linear system with a few linked variables. The MDF also enables iterative refinement so our system can converge to an optimal solution earlier. We chose to do Python because it allows for us to combine all our systems easier because it is able to import MATLAB, has extensive libraries, and has several useful optimization packages. Next. Here you can see the results of our optimization. We ran it 9 different times, each starting at a different airport. As you can see on the right, they each outputted a different profit in result of running it with the linked variables into our optimization model. Next. Here is an analysis of our optimization results. Ultimately, we can see that with the passenger cargo ratio determined by subsystems 3 and the drag coefficient produced by the aerodynamic design of subsystem 2, we get a few different routes that produce the same optimal results. As you can see, they all include LAX, BOS, MCO, and Las Vegas, which each produce a total system profit of 642,905.48 over the set 24-hour period. Next. Now we can go into the sensitivity analysis for our constraints and our parameters. First, the constraint sensitivity analysis. For the amount of time in the day, the coefficient was 46.27. It has a negative sign in front to show it reduced our profits by about 46%. By changing the wing area by about 10%, it increased our profits by 14%. The lift decreased our profits by about 10%. Then, looking at the parameters, the cargo revenue per mile reduced our revenue by 43%, our ground time increased our revenue by 1.28%, and the seat load factor decreased our revenue by about 13.59%. As you can see, the amount of time in the day and the cargo revenue per mile both had a significant impact on our parameters and constraints, and our system was highly sensitive to these variables. Next.
As far as a reality check for our results, ultimately we can see that the profit values we're seeing are plausible and they're in line with what we might expect to see from real aircraft operation. In terms of the routing, it does make logical sense that the most profitable domestic routes would be those that are long cross-country flights, which we can see represented throughout our optimization results. Similarly, we can see from our sensitivity analysis that the constraints and parameters with the largest impact on our system output were the overall time constraint and the cargo revenue per mile. These results, again, make sense when we consider that the amount of the time in a day directly corresponds to how much profit we can possibly produce, and the cargo revenue makes up the largest portion of our profit calculations, so it makes sense we'd see a large effect from that as well. Next.
For the aerodynamic subsystems, the system level optimization changed the constraint we're using the cargo, the whole airplane weight to be the lift to keep the crucial, and also we use the realistic flight condition, change the Mach number and altitude. The drag coefficient is lower than the subsystem only. Next.
As far as looking at subsystem 1 and the comparison between the subsystem only and the larger system, when we took into account the weight balance or the cargo capacity from subsystem 3, the number of seats changed, and the miles per gallon from subsystem 2 also changed as well. So we can see the routes and the total profit changed accordingly.
For the passenger and cargo subsystem, it's noted that the subsystem compared to the overall system actually yields the same result. This is because subsystem 3 is not dependent on the other two subsystems. So you see the number of crew members is the same and the total minimized cost is the same.
Overall, our results seemed reasonable, but we can tell there's room for improvement in the fidelity of modeling within all three subsystems that would ultimately improve our results. For instance, subsystem 1 could be more accurate if we considered more realistic variable demand for specific flights and more realistic timing for different airports. Subsystem 2 could benefit from possibly prototype or generally higher fidelity testing more than just the simulations. And subsystem 3 could get more accurate by considering more realistic variable demand for cargo transportation and more of a reference to the human factor in the loading of the